Hello, honors physics students. We're going to start here by looking at some of the concepts questions from your textbook and the Cutnell and Johnson assignments. Let's start with conceptual question number 1 from the textbook. Asks you to describe the motion of a proton after it's released from rest in a uniform electric field, and then part B talks about the changes in, if any, of energy. Alright, so here I've drawn some oppositely charged parallel plates, so just arbitrarily put the positive plate on the right, negative plate on the left. There's no reason for doing so, I just want to sort of switch it up a little bit. I've drawn my electric field lines all, of course, pointing from positive to negative. It's a uniform electric field. Remember, there's the only way to get a uniform electric field. There's no other arrangement of charges that will do it. And here I put our proton, and of course we know what happens. If I let go, we know what happens. It's going to move this way. But if that's all you said, was that the proton's going to move, that's really not enough. If you said it moves in the direction of the field, that's better, but that's still not enough. That's not really an honors level of an answer. We need more about its motion. So we start off with the idea that, yes, of course, we have a uniform field. Great. A uniform field means that there's going to be a constant force on the proton, right? Fe equals Q times E. The charge is constant, the field is constant, the force is constant as well. From sigma F equals ma, that means it's going to move with a constant acceleration. Now we have something more. It's not just going to move, it's going to accelerate. And just saying move and saying accelerate, they're not the same thing. Right? It's not just moving, it's accelerating. And since it starts from rest, that means it's speeding up. And so now we have a complete answer. It's speeding up in the direction of the field. That makes sense. In fact, really speeding up in a straight line in the direction of the field. That makes sense. That's even better. That's really the best version of this answer at an honors level. How about letter B? What about any changes in energy? Well, the electrostatic force we know is a conservative force. There's only conservative forces acting. We can do conservation of energy, and we know for conservation of energy, there's going to be a gain of kinetic energy from a loss of potential energy. That happens all the time, right? So it starts from rest, it's going to be losing potential energy, going where it wants to go, right? If this is the top of the mountain, this is the bottom of the mountain, it's going to a lower potential, it's going where it wants to go down the mountain, like our cooler of food. And of course, when it loses electric potential energy, it gains kinetic energy. So any statement of conservation of energy saying that it gains kinetic energy and loses potential energy, that would be a good explanation here. Alright, let's go to the Cutnell and Johnson focus on concepts question. Taking number 2, we've got these two different charges placed in two different locations. One charge at each location. The question is, do they have the same electric potential energy? If they have the same electric potential. Let's just go through some of the choices first and see if we can eliminate anything. So A, yes, okay, electric potential energy is also the same, regardless of the type, positive, negative, or the magnitude of the charges. Okay, so I'm not really sure about that, because remember, potential is this very weird concept, and maybe you're not quite sure exactly how it works, and I get that. I have to admit that I didn't really I really understood electric potential until I was in college, and I'm trying to make all these analogies to help you understand it, but if it's still kind of confusing to you, I get it. Remember, though, every time we think about potential, we're visualizing the mountain, so, alright, let's come back to that. Letter B, electric potential energy are just different names for the same concept. Okay, I'm really glad this choice is here, because if you did choose choice B, you're very confused. But it can be confusing, I get it. The word potential and the phrase potential energy, well, they sound an awful lot alike. And yet, that was one of the first things I said about potential, is that it's not potential energy. It's something different. So if you're still confused and think potential energy are the same thing, you're confused, and you've got to get that out of your system immediately. Go back and review the definitions. Letter B is definitely out. They're just not the same thing. Okay. Letter C and D both say no, but for different reasons. Letter C is about electric potential energy does not depend on the charge. Potential does. Letter D, sort of the reverse. Alright, so let's go through it. We know we have a relationship between the two terms here. This is delta V equals delta PE over Q. And immediately we see that there's no way that potential and potential energy are the same thing. So that's very good justification why letter B is incorrect. Okay, there's different things. Now, here we're only talking about a change in potential, so we're talking about the potential itself, so we can get rid of the deltas. We can say the potential is potential energy per charge. That's a good way of thinking about it. Energy per charge, right? That's what potential is, energy per charge. Okay, so letter A says that the potential energies are also the same regardless of the type, positive, negative, and magnitude of the charges. Well, this equation says that's clearly wrong, right? The potential is the same, and if the charges are different, there's no way this electric potential energy can be the same. Not only would the magnitude be different because it says they have different charges, but there's no absolute value here. So even if they are the same magnitude, if the sign is different, there's no way they can have the same potential energy, so letter A is out. So we're down to letter C or D. So we know the answer is no, but the answer is why is it no? So letter C says the potential depends on the charge placed at that location. Okay, so now we have to really know the terms in this equation. We define lowercase q here as the moving charge. And if you go back to your definitions, we also said it's the one not creating the potential. It is not the one responsible for the potential. Okay? Just like the mountain is the thing creating the change in elevation, the cooler is not. The cooler of food is experiencing the change in height up and down the mountain. And that cooler of food is this lowercase q, the test charge, the moving charge. And so it is not responsible for creating the potential. So C is out. It is definitely letter D. right? Electric potential energy at a given location depends on the charge as well as electric potential, and that's all right here in this equation. So hopefully you chose D as well. Let's go on to number 4. All right, we got oppositely charged parallel plates, letters A and B. We got a proton in letter A. We got an electron in letter B. We want to know how is the change in proton's electric potential energy compared to the change in electron's electric potential energy. Okay, well, as always, we want to go with equations. We've been doing this all year long. If you're doing these conceptual questions and you're not referring to equations, you're more than likely not doing it correctly. At least you're not doing it fully correctly. Almost always, you want to be using equations to justify your thinking, justify your reasoning. So here's the equation I want to look at. That change in electric potential energy is Q delta V, and of course the delta is always split up into final minus initial. So all we're going to do is we'll break it down bit by bit. Let's take a look at the proton. Its change in electric potential energy is its charge, and I'm here replacing its charge with the elementary charge. It's one elementary charge, so it's E. And the final minus initial, well, it says it started at A and ended at B, so it's going to be VB minus VA. So it's going from A to B. Here's the final, here's the initial. Great. What about the electron? We do the exact same thing. Its charge, however, is negative E. Remember, there's no absolute value on the charge in these equations. The sign does matter, but it started at B and went to A, so we have VA minus VB, final minus initial. But hopefully, you see, it doesn't take a whole lot of algebra to show that if you distribute this negative sign, these two will flip, and so we get E times VB minus VA, which means these two are exactly the same. And so it is choice A. The change in the proton's electric potential energy is the exact same as the change in the electron's electric potential energy. But let's just go through some of the other choices and see if they don't make sense, right? Letter B, proton experiences greater change in potential energy, so there's greater charge magnitude. Well, that doesn't make any sense. No. Remember, from the very beginning of electrostatics, we established the idea that the exact amount of charge on the proton is the exact amount of charge on the electron. Amount, magnitude, right? Don't worry about the sign. But so here it's saying it has a greater charge magnitude. B is out. C also talks about here has a smaller charge magnitude. That's out. So B and C are immediately out. D talks about the fact that the proton has a larger mass than the electron. Okay, so that sounds really good because it's absolutely true. The proton definitely has a larger mass, which means it's going to be going slower. So it seems like it should have a smaller change in electric potential energy since it's going smaller. It's going slower, but we're talking about potential energy, not kinetic energy. This refers to kinetic energy, mass and speed, although in the end, turns out they actually balance out. But it seems like a good answer, but it's also a bit misleading there because we're not talking about kinetic energy, we're talking about potential energy. And letter E is a really good choice here to look at because it talks about the fact that we move in opposite directions. So if you chose choice E, you've confused yourself. You've forgotten the idea that energy is scalar. There's no directionality to it at all. And yes, I know we often deal with positives and negatives, but that's about the change in energy. An object can gain energy, that's a positive change in energy. An object can lose energy, that's a negative change in energy, but that has nothing to do with actual direction. These are scalar quantities, and it doesn't matter if they're going opposite directions, and they are going opposite directions, but that has nothing to do with it whatsoever. There's no actual directionality to energy. Energy is a scalar quantity. But in the end, of course, the equations definitely show you that A is the correct answer.